Good afternoon, everyone. Thank you for coming. And today I'm going to talk about an observation and model-based analysis of meridional transport in the South Atlantic. I have been working on this project with Claudia and George for about a year and 2 months now. And so we recently have submitted a manuscript based on this work to JGR Ocean. So let me. So the outline of the talk is, at first I'm going to talk about previous studies and motivation, then the objectives, then data and methods, then results, and finally conclusions. So Atlantic meridional overturning circulation is a northward flow of warm water to the north that goes there and sinks and then returns back to the south, resulting in net heat transport to the north. Atlantic meridional overturning circulation plays an important role to the overall global energy balance, and AMOC is also AMOC, that is Atlantic meridional overturning circulation, is believed to be directly linked to several climate phenomena such as fast anomalous climate change, hurricane intensity in the North Atlantic, etc. North Atlantic is relatively well sampled, but South Atlantic is not. So there are like very few studies in this region, observational studies in this region. And so what happened, beginning in 2000, there were like efforts to put some instruments over there and measure meridional overturning transport, heat volume and heat transport, nominal to 35 south and at other latitudes as well. In this slide, I'm basically showing you results by Garzoli and Ranger 2007, by Downritter 2009, and then by Garzoli till 2013. So all of these studies estimated meridional heat and volume transport using XBT transits. And XBT stands for expandable basin thermograph. Generally, what is done, they are thrown from a ship, typically from a ship, and it's capable of measuring temperature from surface to a depth of 1,000 meters. So based on this data, previously all these authors, they estimated this series and this volume and heat transport means. So we kind of like see in the lower left results from Garzoli and Ranger that shows volume and transport is kind of like decreasing from around 0.7 towards 0.4 petawatt when you come from southernmost, which is minus 38 degrees south to 30 south. And there are like a lot of variations in that too. And in blue is geostrophic transport, and in red is the total transport. And these are the time series that shows you both meridional overturning circulation, that's the volume circulation, volume transport, as well as the heat transport in red. And you can see the variability over there too. So the study by Dong 2009 used XBT data nominal to 35 south, and then they found a very strong correlation between meridional volume and heat transport. And the slope line is kind of like 0.06 petawatt per square drop. So it means if we increase meridional volume transport by 1 square drop, there is going to be a change of 0.06, not change, an increase of 0.06 petawatt heat transport. And they also found that both geostrophic and contributions are important, and they show annual cycles, but these cycles are not. Also, studies by Dong et al. 2014, they use a blended product which uses arco-acidic as well as surface height, and then they presented the results for 35 south. Again, observation to the left.
You want to ask them to mute.
Okay. Can you please mute? Okay. All right. That's it. Okay.
If you're on the phone, tell them like.
Am I on the phone? Can you hear me? Can you please mute it? Okay, so in this slide we are kind of like seeing results by Dong et al. 2014, and on the left side of the figure we see observation, and then there are like two different models, one CCSM4 and the other is GFDL model. So what we are seeing here is the importance of geostrophic and Ekman transport. And we see that Ekman and geostrophic parts, which are shown in green and red, both are important to the total transport in observation. But in the model, looks like the Ekman transport plays a major role, not the geostrophic one. So this is a recent study by Dong et al., again using the same satellite and temperature data, a synthetic product, and then they showed it. The time series is shown for January for 2002, I guess, to up to 2012, and what they have shown here, how well their time series match with the previous XVT observations, and which does a very good job. And they also show annual cycles or seasonality of the product at different latitudes, starting from 20 south to 34.5 south. And we find like a very strong annual cycles present in all of these latitudes. And it's kind of like it shows that both Ekman and geostrophic are important at all the different latitudes. So giving this perspective, these are the objectives for this study: to present new estimates of transports using Argo observations between 2000 and 2014 in the South Atlantic. Number 2 is to provide and compare transport estimates from observations and 3 different global models with data assimilation. And number 3, to analyze contribution of boundary currents to the total volume and heat transport. Data and methods. So the method has been described by Claudia many times, but I'll still go. This method follows mid-2014 methodology. What I do here, we use Argo observations and sea surface height field to construct a 3-dimensional velocity field using the methodology. And from now on, I'll call this velocity field as Argo and SSH. What we exactly do, we estimate monthly dynamic height from temperature and salinity profile. Then we use SSH field to derive a synthetic dynamic height field, because Argo observations are sparse, so we want it in a much finer grid. So then finally, zonal and meridional component of geostrophic velocity are estimated using a thermal wind balance to a level of no motion set at 1000 decibar. And then absolute geostrophic fields are obtained by adjusting relative velocity with the velocity obtained from Argo from the flow trajectory. And finally, this is whatever we have done so far is the geostrophic part. Finally, the Ekman part is added to it using NSEP2 winds for this study. This is the data that is up to date, I think, like this, updated yesterday. So it's like 3,918 floats are currently available in the global ocean. And so the data that whatever I'm going to show here, the data is used up to 2014, starting from 2000. And the other 3 model products that we are using is HiCOM-D analysis, SODA, and NSEP. Among the 3 products, HiCOM has fairly good resolution, both in the horizontal and even the vertical, I would say. And the degree that is like 0.08 degree. And the time period of the data is from 2000 to 2012 for HICOM, for SODA is 2000 to 2008, and for INSEP, GODAS is 2001 to 2013. Argo and SSH similarly is known, the fields from Argo and SSH is similarly known for like every 0.5 degree, and the fields are available from 2000 to 2014. First, we show the agreement of the 3D velocity product with drifter data. So from the panel on the side, on the left hand side, shows a climatology of meridional velocity from drifter in blue and Argo in black. So, and the shading are the standard deviation, and it's like plotted for 35 south, and x-axis is showing us longitude, and the panel below shows us the number of drifter observations available in that region for a particular latitude. So you can like see from this this plot that the velocity product that we created is doing a fairly good job, and there are like some dissimilarities that can arise of multiple reasons, potentially maybe due to the difference between the products, aliasing in areas with relatively few drifter observations or few Argo observations near boundaries, which can be really tricky to deal with, because we want to estimate the correlation between SSH field and dynamic height, and that makes, if you do not have lot of measurements available, that becomes very tricky. On the right hand side, I show the same thing for different months, which also shows a fairly good agreement between these two products.
How do you define fairly good agreement?
By fairly good agreement, I mean they within the standard error they match, within the standard deviation they match.
Observation.
Yeah, of the observation. Yes. So this slide is showing us correlation between MOC strength and MHT. That was previously shown by Dong et al. In 2009 paper. So what we are showing here is the all data scattered for 35 south, 30 south, 25 south, and 20 south. And we see a very good correlation between them, between MOC strength, which is plotted on the x-axis, and MHT, which is meridional heat transport, on the y-axis. And the slopes seem to be equal between 35 south and 25 south. They are fairly matching well. It's like almost the same, 0.46 and 0.45 in 25 south. But when you go to 20 south, the slope changes to 0.056. So it means that same amount of heat is transported, meridional heat is transported for 1 square of change in meridional volume transport between 35 south to 25 south. When you go further north, which is at 20 south, the value changes and it becomes more. So this result kind of agrees with the results reported by Dong et al. 2015, but there are like some differences too. Okay, let's come to the time series plot. So these are two time series plots. On the top, I'm showing meridional overturning circulation, which is the volume transport, and the lower panel is meridional heat transport for 30 south on the left and 35 south on the right. And below are the statistics, which are like the mean value and the standard deviation in plus and minuses. So let me talk about first the plot on the right, which is at 35 south. So the pink or the magenta color is showing AX18 measurement, and Argo and SSH is in black, HICOM is in red, SODA is in cyan, and NCEP GODAS is in blue. So So it's a good agreement with all the estimates, especially at 35 south, with similar means. Like 20, the means are like 20 for Argo and SSH is 20 squadron. HICOM is about like 16 squadron, and Soda is 15. NCEP is in the lower side, which is 13. And the heat transport also varies. Argo and SSH is 0.66 petawatt, which is slightly higher than HICOM or NCEP, but it's like reasonable with Soda, because like Soda is 0.52 and Argo and SSH is 0.6 almost. And this is also consistent with the studies by Dong 2015 or with Curzon. On the left, we show the statistics for 30 south. Again, there is a very good match between HICOM and Argo and SSH, which are the mean values are almost like the same, which is about 24 squadron. And heat transport for Argo and SSH is slightly higher, which is 0.76. And whereas HICOM is 0.66 and Soda is even lower. And the lowest one is NCEP GODAS, which is 0.4. And we can see here the seasonality very well. And there is a sharp drop in the HICOM transport at 30 south. I would like to point the left-hand side top panel. There is a drop of HICOM, in NCEP GODAS Meridional volume transport. That drop is about 7 squadron from 2004 to 2005, and then it becomes stable with a mean of 10 squadron. Before that, it was like about 15 to 17 squadron. We do not see that in any other models or in the observations. A similar time series are shown for 20 south and 25 south, and the statistics are in the below. So a similar drop again is seen in the NCEP GODAS between 2004 and 2005, whereas that is not seen. And a very good agreement is observed at 20 south for all the products and the observations. From the right, there is a marked difference between observations and the models, and which is about, I would say, like almost like a 10 squadron, which is a lot. So we are still trying to understand why is this, why this big gap. But whatever we do, we get that value. Talking about the mean heat transport, looks very similar with HICOM and a little bit like lesser than Soda, because Soda is 0.75. I'm talking about 20 south. And when we come to 25 south, heat transport is a lot in Argo and SSH, which is 0.92. And Soda is fairly small, like almost 0.3 petawatt smaller than Argo and SSH. And NCEP is even smaller, like almost half of it. No, not even half, 1/3 of it. I do not show any HICOM plot for 25 south because HICOM has a weird issue at 25 south. It has like very strong barotropic velocity all over. I have a slide later on that I can show. So this is a plot showing seasonality between models and observations and how they are compared. So what I'm showing here in this plot, on the x-axis I have months, different months, and the y-axis I have MOC anomalies. For black is showing Argo and SSH, red is HICOM, blue is NCEP GODAS, and cyan is again Soda. From all these four figures, it's very clear that all the models show annual cycles, whereas Argo and SSH show annual cycles at 35, 30, about 25 also is an annual cycle, but not at 20. And there is a significant difference between the phasing of Argo and SSH anomalies and NCEP and other model anomalies. So, and the shading is also showing us the standard error, which is 95. So I showed here 95% confidence interval. So there are a lot of differences between models and observations for sure. And one thing, our results match, like to some extent, match with DOM 2015, where they use Argo blended product too. To dig it even more, how well the observations and models perform. So what I have done here, I have estimated cumulative volume and heat transport, and I have integrated it from the east towards west. And when I show this plot, it's very clear there are like lot of differences between observations and models in all different latitudes, starting from 20 to 35 south. One visible thing is the HICOM result. HICOM has a very large negative transport at the eastern boundary. So, and you do not see it in any other models or observations.
Yes. Quick question: the volume transfer is sea surface to sea floor?
Sea floor, yes.
Have you looked at this in the upper limb of the animal?
Yes, I did. And
that might help to understand why at some latitudes the mean is so large in Argo.
Yes, yes. Yeah, I have seen that. I'll talk to you about that. Yeah, sure. So so the take home from here is like observations and model are very different, and so we need more study. HICOM is in red.
Yeah, but at 35 we know that's recirculation.
Yes, yes.
Right. So I was surprised that you didn't use it at 20, but you used it at 35.
You mean like, oh, okay.
Okay.
Yeah. And in 25 south I didn't show again because of the same barotropic component. So let's talk about the sectional transport. What I have done here, on the left, I have volume transport for eastern boundary, which is defined as east of Greenwich Meridian, interior, and western boundary, which is defined west of 48 west, and interior is in between these two extremes. So it's a time series. The top plot is the eastern boundary, the middle one is the interior, and the lower one is the western boundary. So again, the colors are the same. The red is HICOM, blue is NSF, cyan is soda, and black is Argo and SSH. So again, you can see like there are a lot of differences between them, and the magenta color are AX18 transits. So UVT, which is the upper limb volume transport for the eastern boundary, they match with AX18 and soda. Because if you think of the statistics which is shown on the right, Argo and SSH is 33.65 square, whereas soda is also 32.13, whereas the other estimates are relatively smaller. And when you go to the interior, mean volume transport from Argo and SSH is very similar to AX18, but lower than HICOM and soda. And in the western boundary, again, mean UVT from Argo and SSH are close to the values from AX18 and soda, and HICOM, mean UVT from NSF is relatively smaller than the others. So the take home is like they are very different. And this is again the meridional heat transport for each section. And again, you see Argo and SSH in the eastern boundary has like almost 1, which matches with HICOM, which is 0.94. Soda is extremely higher, 1.61, and NSF Godas is in between. Like NSF Godas also match with Argo and SSH. Interior again the same story, but like all of them kind of show the same heat transport, which is 0.61, 0.67, and again 0.61. But NSF is the exception. Again, it's 0.45, which is very small. You have the same story again in the western boundaries. When you add it up, it gives you a reasonable value, which is not very different than the observation. So like each section may have different transports, but when you add it up, the whole thing gives you a reasonable value, which somehow match with the observation. So you also try to look at the wind-driven transports at 35 south. We used, we kind of like estimated both Ekman and the geostrophic part of it, and we found Ekman part is very small compared to the geostrophic part, both for the volume transport and heat transport. So next, what we have done, we estimated volume transport and heat transport using different wind products. The wind products that are used here are INCEP 2 winds, ERA interim winds, and Atlas winds. So the estimates are not very different. Yes, estimates are not very different. They're like somehow close. Okay, so small ones like there. So the conclusions are 15-meter velocities from Argo and SSH agree quite well, quote unquote, with those from the surface drifters at 35 south. And I also like try to plot some maps from surface drifters, the Brazil current region and Benguela current region. I have seen like very good similarities with the currents derived from Argo and SSH. Mean transport from Argo are quite consistent with the previous observational study by Garzoli and Dong, but are slightly higher than the model estimates at some latitudes. Volume and heat transport at the boundary and in the interior not only differ from those derived from Argo and SSH, but there are differences between them too. Seasonality from Argo and SSH and models differ in phasing, peak-to-peak amplitudes too. Models mostly show annual cycles at all the latitudes, whereas Argo and SSH exhibit annual as well as weak semi-annual cycle at 20 south. Meridional heat transport and meridional overturning circulation strength maintains a strong linear relationship at all the latitudes, and it's about the same amount of heat is being transported the southernmost latitudes, which are 35 south, 30 south, and 25 south, for 1 square drop change in meridional volume transport. And I have not seen any noticeable trend in the estimates from Argo and SSH. Only INCEP has shown some trend. I will not even say trend, a drop. All right, so this is all I have.